Can a computer decide whether a sentence is true? It can, but only when the sentence is written in a language with no room for doubt. That language is logic, and this is where we build it. Welcome to Discrete Mathematics. This is Chapter 1, Part 1, Propositional Logic. We build the language of logic from the ground up, starting with sentences that are either true or false. Everything else in this course, and much of how a computer decides things, sits on top of this one idea. Let's begin. Let's look at the whole map of the chapter so you can see where we are going. It has three big parts. The first part is propositional logic. This is the logic of whole statements that are true or false. We start here today. The second part is predicate logic. It adds words like for all and there exists, so you can talk about many things at once. The third part is proofs. That is where you learn the accepted ways to show that something is true. We are standing at the start of part 1. Now we zoom into the first part. Propositional logic has three pieces of its own. First, the language. The connectives, the truth values, and the truth tables. This is where we spend this section. Second, applications. We use logic to translate English, to write system rules, to solve puzzles, and to build circuits. Third, logical equivalences. That is where we learn when two statements always agree. We start at the top left with the language. Section 1.1. Propositional logic. This is the foundation section, where we meet the propositions themselves and the 5 basic connectives that join them. Let's look at the plan for this section, so you know what is coming. First, we define what a proposition is. That is our building block, and everything rests on it. Then we meet the 5 basic connectives, one at a time. Not and or, the if-then, and the if and only if. Along the way, we look at 3 cousins of the if-then. Its contrapositive, its inverse, and its converse. Finally, we learn to organize all of it with truth tables. Let's start with propositions. A proposition is a declarative sentence that is either true or false. It must have one definite truth value, and never both. Look at the left column. The moon is made of green cheese is a proposition. It just happens to be false. 1 plus 0 equals 1 is a proposition, and it is true. Now the right column. Sit down is a command, not a statement of fact, so it has no truth value. What time is it is a question. And x plus 1 equals 2 looks like a statement. But it depends on the value of x sentences with free variables are not propositions until we pin the variables down. To do logic, we need names. We use lowercase letters p, q, r, and s as propositional variables. Each one stands for some proposition. We also keep capital T for always true and capital F for always false. From these simple pieces, we build compound propositions using connectives. 5 of them are our basic kit, so let's meet each one. Negation, the not symbol, flips a truth value. Conjunction, the in symbol, is like a wedge pointing up. Disjunction, the or symbol, is a wedge pointing down. Implication is the arrow, and we read it as if then. And the biconditional is the double arrow, read as if and only if. Later we add one more connective, exclusive, or which we can build out of these 5. The simplest connective is negation. We write the not symbol in front of p, and we read it. Not p, it just flips the truth value. Look at the table. When p is true, not p is false. And when p is false, not p is true. That is the whole rule. For example, if P is the sentence, the earth is round, then not P is, the earth is not round. Negation takes one proposition and gives back its opposite. Conjunction means and. We write P and Q with the wedge that points up. The rule is strict. The whole thing is true only when both parts are true. Row 1. P is true and Q is true, so P and Q is true. This is the only row that gives true. Row 2. P is true but Q is false. One part fails, so the whole thing is false. Row 3. P is false and Q is true. Again, one part fails, so the answer is false. Row 4. Both are false, so the answer is false as well. For example, I am at home and it is raining is true only if both facts hold at the same time. Disjunction means or. We write P or Q with the wedge that points down. This or is generous. It is true when at least one part is true and both parts is fine too. Row 1, P is true and Q is true. At least one part is true, so P or Q is true. Row 2, P is true and Q is false. One true part is enough, so the answer is true. Row 3, P is false and Q is true. Again, one true part, so the answer is true. Row 4, both are false. Nothing is true, so this is the only row where P or Q is false. So I am at home or it is raining is false only when I am not at home and it is not raining. Be careful. The English word or can mean two different things, and only one of them is our disjunction. The first is the inclusive or. Students who have taken one of these two courses may take the class, and having taken both is also fine. That is exactly our down wedge. The second is the exclusive or. When a waiter says, soup or salad comes with this meal, you get one, but not both. We write it with the plus in a circle symbol and we call it XOR. Let's read the table for exclusive or one row at a time. The rule is exactly one of the two must be true. Row 1. Both P and Q are true. Exclusive or gives false because you may not have both. Row 2. P is true and Q is false. Exactly one is true, so the answer is true. Row 3. P is false and Q is true. Again, exactly one is true, so the answer is true. Row 4. Both are false. Nothing is true, so the answer is false. Now compare with the inclusive or. In the top row, exclusive or gives false, while inclusive or gave true. That one row is the whole difference between them. Exclusive or is an extra connective on top of the 5, and we can build it from them. P exclusive or Q is the same as open bracket P or Q close bracket, and not open bracket P and Q close bracket. This connective is the conditional. We write P arrow Q, and we read it out loud as if P then Q. Row 1, P is true and Q is true. The promise holds, so the conditional is true. Row 2, P is true but Q is false. This is the one and only row where the conditional is false. Row 3, P is false and Q is true. The conditional is true. Row 4, P is false and Q is false. The conditional is true again. Those last two rows may surprise you. When P is false, the conditional is true no matter what Q is. The next slides will show you why this makes sense. The two sides of an arrow have names and books use several. The left side, P, is the hypothesis. You will also see it called the antecedent or the premise. The right side, Q, is the conclusion. Some books call it the consequence. All these words mean the same thing. An example, let P mean I am at home. Let Q mean it is raining. Then P arrow Q reads. If I am at home, then it is raining. The two parts have nothing to do with each other, and that is allowed. Now the strange part of the conditional. In everyday speech, if then suggests the two parts are related, like a cause and an effect. In logic, there is no such rule. Look at these three sentences. Each one starts with a false hypothesis. The moon is made of green cheese. 1 + 1 = 3. Both of those are false. Because the hypothesis is false, logic says the whole conditional is true. It sounds silly, but it is consistent. The next slide gives a picture that makes this feel natural. Think of a conditional as a promise or a contract. Someone gives you their word, and you check later whether they kept it. If I am elected, then I will lower taxes. When is that promise broken? Only if the person is elected and then does not lower taxes. If the person is never elected, you cannot accuse them of breaking the promise, whatever they do about taxes. One broken promise row is false, and every other row is true. This matches the truth table exactly. English gives us many phrasings for the same conditional. P*Q, let's read them slowly. Some are easy. If P, then QQ if PQ whenever PQ follows from P, these all put the arrow where you expect it. But a few of them are traps. P only if QP is sufficient for QQ is necessary for P. We look at those on the next slide. Two phrases catch almost everybody. Let's take them one at a time. First, P only if Q the word order tempts you to flip the arrow. Do not. P only if Q still means P*Q. Second, the word sufficient. P is sufficient for Q means P*Q that one behaves as you expect. Third, the word necessary. P is necessary for Q means Q*P the arrow points the other way. So necessary and sufficient point in opposite directions. When you are unsure, first rewrite the phrase as a plain if-then sentence. Then read the arrow straight off it. Starting from one conditional, P*Q, we can build three relatives. Each one changes the arrow, or the two parts, or both. The converse flips the arrow. It is Q*P. The contrapositive flips the arrow and negates both parts. It is not Q*, not P. The inverse negates both parts but keeps the direction. It is not P*, not Q. Remember this slide. Soon we prove that one of these three, the contrapositive, always has the same truth value as the original. Let's watch how we build each one on a real sentence. First, find P and Q raining is sufficient for not going to town means. If it rains, then I do not go to town. So P is, it is raining, and Q is, I do not go to town. Now the converse. Flip the arrow. Q*P in English, if I do not go to town, then it is raining. Now the inverse. Negate both parts and keep the direction. Not P*, not Q in English, if it is not raining, then I will go to town. Now the contrapositive. Negate both parts and flip. Not Q*, not P in English, if I go to town, then it is not raining. The biconditional uses a double arrow, pointing both ways. We read P*Q as P if and only if Q it is true when the two sides match. Row 1. Both are true, so they agree, and the biconditional is true. Row 2. P is true and Q is false. They disagree, so the answer is false. Row 3. P is false and Q is true. They disagree again, so the answer is false. Row 4. Both are false. They still agree, so the answer is true. So the double arrow is really asking, do these two agree? The two true rows are the top and the bottom of the table. The biconditional shows up in several English phrasings, and they all say the same thing. P is necessary and sufficient for Q. Notice both words together, necessary and sufficient. That pairing is the signal. The last line is the short form that mathematicians write. It is spelled IFF with two F's. Those two F's stand for if and only if. The two sides go up and down together. This slide is the recipe for building a truth table by hand. Two things to plan: the rows and the columns. For the rows, you need one row for every way to assign true and false to the basic pieces. With two pieces, that is 4 rows. With 3 pieces, 8 rows. For the columns, start with the atomic propositions on the left. Then add one column for each small piece as the expression grows. The final column, on the far right, is the whole proposition. Building it piece by piece keeps you from making mistakes. Let's build a full truth table for P or Q, arrow, not R. 3 pieces P, Q, and R, so we need 8 rows. We take them 4 at a time. First, a warning about grouping. There are no brackets, so precedence decides. Not binds first, then, or then the arrow. So this means bracket P or Q, close bracket arrow, not R. Row 1, P, Q, and R are all true, not R is false. P or Q is true, so we have true arrow false, and that is the one case where an arrow fails. The answer is F. Row 2, R is now false, so not R is true. P or Q is still true. True arrow true is true. Row 3, Q is false, but P is true, so P or Q is still true. R is true, so not R is false. True arrow false is false again. Row 4, R is false, so not R is true. True arrow true, so the answer is true. Notice the pattern already. While P is true, P or Q is always true, so the answer just follows, not R. Now the 4 rows where P is false. Something new happens here, so watch the hypothesis column. Row 5, P is false but Q is true, so P or Q is still true. R is true, so not R is false. True arrow false is false. Row 6, R is false, so not R is true. True arrow true is true. Row 7, now P and Q are both false, so P or Q is false. An arrow that starts from a false hypothesis is true, so the answer is true. Row 8, P or Q is false again and R is false. The hypothesis still fails, so the answer is true. That is the lesson of this table. Once the hypothesis fails, the conditional is true. It does not matter what is on the right. Two propositions are equivalent when they agree in every single row of the truth table. Let's test a conditional against its contrapositive. Row 1, P and Q are both true. P arrow Q is true. Not Q arrow not P is false arrow false, which is true. They agree. Row 2, P is true and Q is false. P arrow Q is false. On the other side, true arrow false is also false. They agree. Row 3, P is false and Q is true. P arrow Q is true and false arrow true is true. They agree. Row 4, both are false. P arrow Q is true and true arrow true is true. They agree again. All 4 rows match, so the two statements are equivalent. This is useful. To prove if P then Q, you may instead prove if not Q then not P. Now the opposite job. Let's show that two statements are not equivalent. We compare P arrow Q against its inverse and its converse. To prove non-equivalence, we only need one row where the truth values disagree. Look at the shaded row. P is true and Q is false. There the implication is false. But in that same row, the inverse is true, and the converse is true. One mismatch is all it takes. The implication matches neither of them, and that is a very common mistake in everyday reasoning. A counting question. A truth table lists every combination of true and false for the variables. So within variables, how many rows do we need? The answer is 2 to the power, and each variable can be true or false. That is 2 choices, and within independent variables the choices multiply. So one variable gives 2 rows, 2 variables give 4 rows, and 3 variables give 8 rows. Chapter 6 proves this carefully. And a deeper point. Each row can independently be true or false in the final column, so the number of truly different propositions is 2, raised to the power 2 to the n. That is very large, but still finite. When you write a formula without parentheses, the reader and the computer both need a rule to decide what groups with what. This table gives that rule. Negation, the not sign, binds tightest. Its precedence is 1, so it grabs its operand first. Then comes and with precedence 2. Then or with precedence 3. Then the conditional arrow with precedence 4. And last, the double arrow with precedence 5. A smaller number means it grabs its operands first. Let's read this formula together. P or Q arrow, not R, there are no parentheses, so we use the table. Or has precedence 3 and the arrow has precedence 4. Smaller binds first, so or grabs its 2 operands before the arrow does. The formula reads as bracket P or Q, close bracket arrow, not. Now be careful. If you meant P or in brackets Q arrow, not R, you must write those brackets yourself. When in doubt, add parentheses. They cost nothing and remove all confusion. Section 1.2. Now we turn from the machinery of logic to what logic is for, and we apply the same tools to real problems. Let's look at the road map for this section. We apply propositional logic to 5 kinds of problems. First, turning ordinary English sentences into logic formulas. Second, writing precise system specification for software and hardware. Third, Boolean searching, which is the and or not of search engines. Fourth, logic puzzles, which train careful reasoning. And fifth, logic circuits, the gates inside every computer. We take them one at a time. To translate English into logic, do 2 things. First, find the atomic parts and give each one a letter. Second, find the connecting words and match them to logic symbols. Step 1. The first atomic statement is I go to Harry's, call it P. Step 2. The second is I go to the country, call it Q. Step 3. The third is I will go shopping. Notice we write it positively even though the sentence says not go shopping, call it R. Now the connecting words. Step 4. The sentence says Harry's or the country. That or is the disjunction, so we have P or Q. Step 5. It says I will not go shopping. That not is negation, so we have not R. Step 6. The whole sentence has the shape if this then that. That is the conditional arrow, so we get bracket P or Q, close bracket arrow, not R. This example has a tricky phrase, only if. Let A mean you can access the internet from campus. Let C mean you are a computer science major. Let F mean you are a freshman. Now the rule. P only if Q means. If P is true, then Q must be true. So it becomes P arrow Q. Be careful. This is not Q arrow P. Only if marks the necessary condition, and the necessary condition goes on the right of the arrow. So the whole thing is a arrow, bracket, C, or not F read aloud. If you access the internet, then you are a computer science major or not a freshman. Engineers must turn vague English requirements into precise logic, so there is no room for misunderstanding. This is one requirement. The automated reply cannot be sent when the file system is full. Let's translate it step by step. Step 1. Find the statements. The first one is about sending the reply. An important habit, always write your letter for the positive version. So let P mean the automated reply can be sent. Step 2. The second statement is the file system is full. Call it Q. Step 3. Now read the connecting words. The sentence says cannot when. The word when here means if. So the file system being full is the condition. That gives us Q arrow something. Step 4. What is the something? The sentence says the reply cannot be sent. That is the negation of P, so we write not P. Putting it together, Q arrow not P read it aloud. If the file system is full, then the automated reply cannot be sent. That is exactly what the requirement said. Consistent means we can pick true or false for each variable so that all requirements hold at the same time. If no such choice exists, the requirements contradict each other, and that is a bug in the design. Requirement 1. The diagnostic message is stored in the buffer, or it is retransmitted. Requirement 2. The diagnostic message is not stored in the buffer. Requirement 3. If the diagnostic message is stored in the buffer, then it is retransmitted. Are they consistent? We answer in 3 steps. Find the propositions, translate each requirement, then look for an assignment that satisfies all of them. Step 1. How do we find the propositions? Read the sentences and look for the smallest complete statements. A proposition must be able to be true or false all by itself. Look at sentence 1. The diagnostic message is stored in the buffer. That is a complete statement, so we give it a letter. Call it P. Now the other half of sentence 1. It is retransmitted. That is also a complete statement. Call it Q. Sentences 2 and 3 bring nothing new, so 2 letters are enough. And an important habit, the words or not and if then are not part of a proposition. They are the connectives, so leave them out when you assign letters. Step 2. Translate. Take each sentence and swap the words for symbols. Sentence 1 says P or Q the word or is the disjunction, so it becomes P, down wedge Q. Sentence 2 says not P. The word not is negation, so it becomes the negation sign in front of P. Sentence 3 says if P then QF, then is the conditional, so it becomes P arrow Q. The English problem is now a logic problem. Can these 3 be true at the same time? Step 3. Now we look for an assignment. Do not guess randomly. Start with the specification that gives you the least freedom. Specification 2 says not P, so P must be false. Now try Q true and check every specification. Specification 1 is P or Q substitute, false or true, that is true. Specification 2 is not P, substitute not false, that is true. Specification 3 is P arrow Q substitute, false arrow true. An arrow that starts from false is always true, so this is true. All 3 are true at the same time. We found an assignment that works, so the specification is consistent. Now watch what happens when we add one more requirement. The message is not retransmitted. In logic that is not Q. Follow the forcing. Specification 4 says not Q, so Q must be false. Specification 2 says not P, so P must be false. Now look at specification 1. It says P or Q for an or to be true, at least one side must be true. But we just forced both P and Q to be false. So there is no way out. No assignment works, and the four requirements contradict each other. This is what inconsistent means, and we found a bug before anyone wrote a line of code. These puzzles come from Raymond Smullyan. On this island, everyone is one of two types. A knight always tells the truth. A knave always lies. You meet two people, A and B. A says B is a knight. B says the two of us are of opposite types. What are they really? Let's set up the letters. Let P mean A is a knight. Let Q mean B is a knight. B's claim that the two are of opposite types is written as P and not Q, or not P and Q. Step 1. Let's try the first case. Suppose A is a knight, so P is true. Step 2. Knights tell the truth. A said B is a knight, so Q is true. Step 3. B is a knight too, so B also tells the truth. That means B's claim must be true. Step 4. But look. With P true and Q true, both are the same type. So B's claim that they are opposite types is false. We have a contradiction. Step 5. The first case fails. So it is not a knight, which means A is a knave. Step 6. Knaves always lie. A said B is a knight, and that is a lie, so B is not a knight. The answer, both A and B are knaves. Every computer is made of tiny switches. In a circuit, each wire carries one bit. 0 means false, and 1 means true. From just 3 basic building blocks, called gates, we can build any digital circuit. The first gate is the inverter, also called the NOT gate. It takes one bit and flips it, so the output is not P. The second is the OR gate. It takes 2 bits and outputs P or Q, the disjunction. The third is the AND gate. It takes 2 bits and outputs P and Q, the conjunction. To build a bigger circuit, take the output formula, build a small circuit for each piece, then connect them. Let's do it for P and not Q, or not R. Send Q through a NOT gate to get not Q, then feed P and not Q into an AND gate, and that gives you P and not Q. Send R through a NOT gate to get not R, finally feed those two into an OR gate. The output is P and not Q, or not R. Section 1.3. Propositional Equivalences. Two propositions are equivalent when they always have the same truth value, and now we learn the laws that let us rewrite one as another. Let's look at the plan for this section. First, we define 3 kinds of proposition: tautology, contradiction, and contingency. Then we study logical equivalence, which means 2 propositions always agree. We learn the important laws and how to use them to show 2 propositions are equal. Finally, we look at satisfiability, and we solve a Sudoku puzzle with logic. 3 important words. A tautology is a proposition that is true for every possible choice of truth values. The example is P or not P. A contradiction is the opposite. It is always false. The example is P and not P, which can never both hold. A contingency is in between. It is sometimes true and sometimes false. A single letter P is a contingency. Read the truth table. The third column, P or not P, is true in every row. The last column, P and not P, is false in every row. 2 compound propositions are logically equivalent when they always agree. Formally, P and Q are equivalent if P if and only if Q is a tautology. We write it with a special equals sign, P equivalent Q, or with a double arrow. The easy test is the truth table. Build the column for each proposition, then compare. If the two columns match in every row, the propositions are equivalent. Let's do exactly that. Let's check one of the most useful equivalences. Is not P or Q the same as P arrow Q? We build both columns and compare them, row by row. Row 1, P is true and Q is true, so not P is false. Not P or Q is false or true, which is true. And P arrow Q is true. They agree. Row 2, P is true and Q is false. Not P is false, so not P or Q is false. And P arrow Q is false, because a true hypothesis with a false conclusion is the one failing case. They agree. Row 3, P is false and Q is true. Not P is true, so not P or Q is true. And an arrow from a false hypothesis is true. They agree. Row 4, both are false. Not P is true, so not P or Q is true. And the arrow is true again. They agree. All 4 rows match, so the two propositions are equivalent. Remember this one. It is the rule we use most often to rewrite an implication. De Morgan's laws tell us how a knot moves across in and or across in or. The first law, not bracket P and Q, close bracket, is equal to not P or not Q when you push the knot inside the and flips to or. The second law, not bracket P or Q, close bracket, is equal to not P and not Q here the or flips to end. These laws are named after Augustus de Morgan, a British mathematician who lived from 1806 to 1871. Let's prove the second law with a truth table. To prove the second law, we build a column for each side, then compare them row by row. Row 1, P and Q are both true, so P or Q is true and its negation is false. On the other side, not P is false, so not P and not Q is false. They agree. Row 2, P is true and Q is false. P or Q is still true, so the negation is false. And not P is false, so the N is false. They agree. Row 3, P is false and Q is true. P or Q is true, so the negation is false. Not Q is false, so the N is false. They agree. Row 4, both are false. Now P or Q is false, so its negation is true. And not P and not Q are both true, so their N is true. They agree. All 4 rows match, so the law holds. The only row where either side is true is the last one, when both P and Q are false. That is what neither P nor Q means. These are the basic identities of logic. Let's read the symbols out loud, one law at a time. The identity laws. P and true is the same as P, because adding a condition that is always true changes nothing. In the same way, P or false is just P. The domination laws. P or true is always true because one side is already true, and P and false is always false. The idempotent laws. P or P is just P, and P is just P. Repeating a fact adds nothing. The double negation law. Not P is just P. Two negations cancel each other. And the negation laws. P or not P is always true because one of them must hold. P and not P is always false because they cannot both hold. Keep this table handy. This second table mirrors the rules of ordinary algebra, so a lot of it will feel familiar. Commutative means order does not matter. P or Q is the same as Q or P, and the same holds for end. Associative means grouping does not matter. You can move the parentheses and the meaning stays the same. Distributive means you can multiply out, just like with numbers. Here it works in two directions, or distributes overend. The other line shows in distributing over or. Absorption is the surprising one. P or the group P and Q collapses back to just P. If P is true, the whole thing is true. And if P is false, the group is false too. These are the equivalences for the arrow, and the first one is the most important rule in this whole chapter. Memorize this line. P implies Q is the same as not P or Q. This single rule turns every implication into an or, which is why almost every proof starts by using it. The second line is the contrapositive. P implies Q is the same as not Q implies not P. We proved that one with a truth table earlier. The last 4 lines of the table all carry the same idea. Two conditionals that share a side can be folded into one. Look at the first line. If P gives Q and P gives R, then P gives both Q and R together. The shared P comes out in front. The second line shares the other side. If P gives R and Q gives R, then P or Q gives R. Either one on its own is enough to give R. The third and fourth lines are the same two shapes with or instead of end. You do not need to memorize these. Recognize the pattern. A shared side can be factored out. Table 8 handles the biconditional, the double arrow read as if and only if. Look at the top line. A biconditional is just two implications joined by end. P implies Q, and Q implies P. That is what if and only if really means, and it is how you prove one. Prove both directions. The other lines say you may negate both sides and the biconditional still holds, and that negating a biconditional is the same as negating one side. Now we use the tables to prove things instead of building a truth table. The idea is a chain. We start with expression A. We rewrite it using one law, and that gives us a 1. Each step must be a valid equivalence. We keep going, one law per line, and we name the law we used each time. When we reach expression B, we are done. A and B are equivalent. One important freedom. In every law, the letters P, Q, and R stand for any proposition, even a big, complicated one. That is what makes this small table of laws so powerful. Let's look at our goal. On the left, we have the negation of a big or. On the right, we have not P and not Q. We want to show these two are the same, and we will not use a truth table this time. Instead, we rewrite the left side, one step at a time. Every step uses one law, and we name that law. When the left side turns into the right side, we are done. We start with the negation of a big, or this is line 0, the expression we were given. Step 1. De Morgan turns not of an or into and of the two negations, so we get not P and not of the bracket. Step 2. We use De Morgan again, this time inside the bracket. Not of an n becomes or of the two negations, so the bracket opens into not P or not Q. Step 3. Double negation cancels. Not P is just P. Step 4. Now we distribute the n over the or. We get not P and P, or not P and not Q. Step 5. Look at the first piece. Not P and P a thing and its own negation can never both be true, so that piece is always false. We write F. Step 6. We swap the two sides of the or. This is just the commutative law, and now F sits on the right. Step 7. Or with false changes nothing, so F drops away. What is left is not P and not Q. That is exactly the right side we wanted, and the proof is done. A tautology is a proposition that is true no matter what. It is true for every assignment of P and Q. We can prove one without a truth table. We rewrite the proposition, one law at a time, until nothing is left but T. If the whole thing collapses to plain T, and we assumed nothing along the way, then the proposition is always true. Line 0 is the proposition we were given. P and Q, arrow P or Q. Step 1 uses the key rule for the arrow. An implication is the same as, not the hypothesis or the conclusion, so the arrow becomes an or. Step 2. De Morgan opens up the knot of the end. It becomes not P or not Q. Step 3. Everything here is joined by or, so we may reorder and regroup freely. We put each variable next to its own negation. Step 4. Not P or P is always true, and not Q or Q is also always true, so both groups become T. Step 5. T or T is just T by the domination law. We reach plain T and we assumed nothing, so the original proposition is a tautology. Now we turn to satisfiability. So far we asked whether a proposition is always true. This time we ask something weaker and much more useful. Is there any way at all to make it true? A compound proposition is satisfiable if we can find at least one way to set its variables, true or false, that makes the whole thing true. Just one working assignment is enough. If there is no such assignment at all, and every choice makes it false, then we say it is unsatisfiable. And a neat link. A proposition is unsatisfiable exactly when its negation is a tautology. If the original is false for every assignment, then its opposite is true for every assignment. Let's test two propositions. To show something is satisfiable, we do not need a truth table. We only need to find one assignment that works. Part it as 3 brackets joined by end. Try setting P, Q, and R all to true. Then every bracket has a true piece, so the whole thing is true. One assignment was enough. Part B has 2 brackets joined by end. Open bracket P or Q or R close bracket. And open bracket not P or not Q or not R close bracket. Pause and try to find an assignment yourself. Okay, let's look. Try P true and Q false. The first bracket is true because P is true. The second is true because not Q is true. Again, one assignment was enough, so part B is satisfiable. Part C joins all 5 brackets together with end. We could check all 8 cases, but there is a better way. Let's read each bracket as an implication. Bracket 1 is P or not Q and or like this says. If Q is true, then P must be true, so it means Q arrow P. Bracket 2 is Q or not R in the same way. It means R arrow Q. Bracket 3 is R or not P. It means P arrow R. Now put the 3 arrows together. P leads to R, R leads to Q, and Q leads back to P. It is a closed cycle, so P, Q, and R must all be equal. Only 2 cases are left, not 8. So only 2 candidates are left. Let's test them. First candidate, P, Q, and R all true. Look at the last bracket, not P or not Q or not R. If all 3 are true, then all 3 negations are false, so this bracket fails. Second candidate, P, Q, and R all false. Look at the fourth bracket, P or Q or R. If all 3 are false, this or is false too, so this bracket fails as well. Both candidates fail and there is nothing left to try, so part C is not satisfiable. We never built a truth table. We reasoned about what the brackets force, and that cut 8 cases to 2. Before the next example, we need short notation for long ors and long ends. The big V symbol with J going from 1 to N means P1 or P2, and so on up to Pn it is one big or over all of them. The big wedge symbol with J going from 1 to N means P1 and P2, and so on, up to Pn one big and over all of them. These work just like the big sum sign for adding numbers and the big product sign for multiplying them. We use them next to write the Sudoku rules compactly. Sudoku is a famous number puzzle. The board is a 9 by 9 grid, so 81 cells in total. It is also split into 9 smaller 3 by 3 squares, and we call each small square a block. At the start, some cells already hold a number from 1 to 9, and the rest are blank. Your job is to fill in every blank cell. 3 rules must hold. Each row must contain every number 1 to 9, each column must too, and each 3 by 3 block must too. Let's put satisfiability to work on a puzzle you already know. We turn a Sudoku grid into one big proposition, and then let a solver find an assignment that makes it true. This is the clever step. We create one propositional variable for every possible fact about the board. We write P of I, J, and it is true when the number n sits in the cell at row I, column J. The row index runs 1 to 9, the column index runs 1 to 9, and the value runs 1 to 9. 9 times 9 times 9 gives 729 variables. For example, in the sample puzzle, the 6 sits in row 5, column 1. So P of 5, 1, 6 is true. But that same 6 cannot appear again in row 5. So P of 5, J, 6 is false for every other column J. Now we write the Sudoku rules as one giant proposition. First, the clues that come pre-filled. For each such cell, we simply assert that P of I, J, n is true. Next, every row must contain every number. Read this formula from the inside out. The big, or over J from 1 to 9, says number n appears in some column of row I the too big, and then cover every value in every row. The column rule works the same way, with rows and columns swapped. The inner big or runs over the rows, saying number n appears in some row of column J, and the outer ends cover every value in every column. 2 rules remain. First, every 3 by 3 block must contain every number. The inner big or say number n appears somewhere in that block, and the outer ends cover every block and every value. The tricky part is naming the cells of one block. We use R and S, each 0 to 2, to choose which block. Then I and J, each 1 to 3, choose a cell inside that block. The row index becomes 3R plus I, and the column index becomes 3S plus J. The last rule stops a cell from holding 2 numbers. We take it over every pair of different values, and every cell. It says, if P of I, J, n is true, then P of I, J, n prime is false. In words, if one number sits in a cell, no other number can. So how do we solve the puzzle? We join all the rules with and into one enormous proposition, then look for an assignment that makes the whole thing true. The variables that come out true spell the solved grid. And that grid really is legal. Take any row. Each of the 9 values must appear somewhere in it, and no cell may hold 2 values. So the 9 values sit in 9 different cells. But the row has only 9 cells, so each cell gets exactly one number, and each value appears exactly once. In principle, a truth table could decide satisfiability, but with so many variables the table is astronomically large, too big even for fast computers. So researchers build clever programs called satisfiability solvers. This matters far beyond Sudoku. Many real problems like scheduling, circuit design, and verification can be rewritten as satisfiability problems and handed to the same solvers. That is where this chapter has been heading all along.